While data preparation and training a machine learning model is a key step in machine learning pipeline, it's equally important to measure the performance of this trained model. How well the model generalizes on the unseen data is what defines adaptive versus non-adaptive machine learning models. By using different metrics for performance evaluation, we should be in a position to improve the overall predictive power of our model before we roll it out for production on unseen data. So once we have trained the machine learning model, then we'll test it on the unseen data. And most important part is for judging the performance of the model is how well it performs on unseen data. So to measure it in quantitatively, we have different metrics. That's the only thing. Without doing a proper evaluation of the ML model using different metrics and depending only on accuracy, it can lead to a problem while the respective model is deployed on the unseen data and can result in poor predictions. So once you've already deployed the model and then you realize that the model is not performing well on the unseen data, then it will create a problem. So this happens because in the cases like our models don't learn but instead memorize, hence they cannot generalize well on unseen data. So the first important metric for a classification problem is confusion matrix. A confusion matrix is a matrix representation of the prediction results of any binary testing that is often used to describe the performance of the classification model or the classifier on a set of test data for which the true values are known. The confusion matrix itself is simple to understand, but related terminology for confusion matrix can be confusing. So this is how we use confusion matrix. So on the x-axis or the top, we have predicted values, the values that predicted by the model, and here we have the actual values. So the first is 0 0 1 1. So here true negative, the values that the model identified negative and were actually negative. So this is why this is known as true negative. Over here this is false positive. The model actually predicted positive or 1 for that outcome, but it was actually negative. So this is the false prediction made by the model. So this is false positive. In this cell we have positive and negative. So our model predicted it to be negative, but actually it was positive. So this is against a false prediction, that is false negative. And over here we have a true positive. So the model predicted it to be positive and actually also it was positive. So this is a correct prediction. So true positive. So true negative, false positive, false negative, true positive. Over here we have values that are predicted by the model, and here we have the actual values. So this is the terminology. Each prediction can be one of the 4 outcomes based on how it matches up to the actual value. So true positive, that is predicted to be true by the model and also true in the reality. True negative, predicted false by the model, also actually false in reality. False positive, predicted true by the model but actually it was false in reality. And false negative, predicted false by the model but true in reality. Now we calculate different metrics from the confusion matrix. So first one is accuracy. Overall, how often the classifier is correct. So accuracy is true positive plus true negative divided by the all 4. So values that were predicted correct by the model and values that were predicted correctly negative by the model, both of them will be considered over here and divided by the total cases that we have. So this is accuracy. Correctly identified divided by total. When our classes are roughly equal in size, we can use accuracy, which will give us correctly classified values. Accuracy is a common evaluation metric for classification problems. It's the number of correct predictions made as a ratio of all predictions made. Precision. Now when it predicts CS, how often it is correct. So when the model predicts CS, how often it is correct. When we have the formula goes like true positive divided by total number of yes predictions made by the model. Again very simple. Truly positive divided by the total number of yes predictions made by the model. When we have a class imbalance, accuracy can become an unreliable metric for measuring our performance. For instance, if we had a 99-1 split between two classes A and B, where just any rare event B is our positive class, we can build a model that was 99% accurate just by saying that everything belongs to class A. Clearly, we shouldn't be building a model if it doesn't do anything to identify class B. Thus, we need different metrics that will discourage this behavior. For this, we use precision and recall instead of just simple accuracy. Recall or sensitivity. Recall is when it's actually yes, how often does it predict yes? So true positive rate, we also recall is also known as true positive rate. That is true positive divided by actual yes. Recall gives us the true positive rate, which is the ratio of true positives to everything else positive. Now, in case of the 99 to 1 split between classes A and B, the model that classifies everything as A would be having a recall of 0% for the positive class. B. Precision would be undefined 0 by 0. Precision and recall provide a better way of evaluating the model performance in case of a class imbalance. So when you have imbalance, or let's say in your output data set, you have a 90 to 10 kind of split or 95 to 5 kind of split. So if you randomly predict class B, which is the 95% of the outcome, then the accuracy of the model will always be 95%. But here, due to data imbalance, precision and recall play an important role. Now ME, which is an important metric for evaluating your regression model. So as seen by the formula, it is very simple. You subtract the value predicted by your model and you from the actual value. Let's say your model predicted the sales forecast of 100, but actually it was 95. So you subtract both of them and you add all the rows, and then you divide by the total number of observations. Here we use the absolute or mod value just in case to avoid negatives. So for example, if the model predicted 95 but the actual sale was 100, so we'll getting a negative value. That's why by taking the modulus of that value, it will convert it to a positive value. Basically the error will be clearly visible. Again, we have one more metric called MSE, mean squared error. Instead of taking absolute value, we take the square of the difference to avoid the negative value. And again, we add all of them and divide by the total number of observations. So these were the two important metrics for regression. I hope you are clear with different model evaluation metrics that we use in machine learning. We'll be using them in lot of in next few videos. So it is important to know this concept. Thank you for watching. Now let's move to the next video.